Hello again. In this video, we're going to begin talking about the material from section 3.9, which is about finding the derivatives of the logarithmic functions and the exponential functions. Now, the way we're going to develop this section is we're first going to find the derivative of the natural log function. And then after we do that, we'll find the derivative of the general exponential function. And after that, we'll develop the derivative of the general logarithmic function. Now, in this first video, I'm just going to lay the groundwork for finding those derivatives. It's important that we review some of the properties of logarithmic and exponential functions before we proceed to find their derivatives. Okay, so let's talk about the natural log function first. The natural log function actually comes from an exponential function. In fact, all logarithmic functions come from some exponential function. They're the inverse of some exponential function. That's where they came from. And so the ln of x, right, the natural log of x, actually is the inverse of the exponential function e to the x, where e is the natural base. Okay, so let's graph e to the x, right? If you graph e to the x, the graph of e to the x looks like this. And so if you want to find the inverse of this function, the idea behind finding an inverse of a function is the input and the output will switch. So for this function, right, e to the x, if you input a 0, e raised to the 0 power is equal to 1. But for the inverse function of this, if you put a 1 in, you're going to get a 0 out. And that's true for every ordered pair on the graph of this function. Okay, so let's try to graph the inverse of this function by switching the x and the y values for each of these ordered pairs. So clearly, this one, instead of being 0, 1, is going to end up being 1, 0 for the inverse of this function, the graph of the inverse of this function. So this point is going to become, on the inverse, it's going to become 1, 0, which is down here. If you do this for every single ordered pair, this is the graph of the inverse. So for example, some point over here, if you switch its x and y value, is going to give you a point over here. Okay, in fact, the easy way to do this is the graph of the inverse function is simply a reflection of this original function across the line y equals x, simply because you're switching the x and the y values. So that's where the natural log function came from. It's simply the inverse of the exponential function e to the x. Now remember, ln of x has a base of e. Right? You could write this as log base e of x, but we just use the symbol ln for the natural log of x. But this means it has a base of e. Okay, now notice that the domain of of e to the x, right, the exponential function e to the x, is minus infinity to infinity, as the domain of this natural log of x function is only positive values of x, right? X has to be positive. It never actually reaches 0. This is actually a vertical asymptote. So x needs to be positive. And so it makes sense to take the natural log of a positive number. It doesn't make sense to take the natural log of 0 because that's not defined. 0 is not part of the domain, and it doesn't make sense to take the natural log of a negative number because negative numbers are not in the domain of this function either. Okay, so having said that, there are certain properties that we should be familiar with before we find the derivatives of exponential and logarithmic functions. So let's talk about these properties. So the first property here says that if you take e and raise it to the ln of x, it's equal to x for all x greater than 0. And I'll show you why that's true in a moment. The second property here says that ln of e to the x is equal to x for all x values. So let's see why this is true. So let's say f of x is equal to e to the x, and its inverse, of course, is natural log of x. Now it's just a property of a function and its inverse. If you take f and compose it with its inverse, then you just get x back. It's also true if you change the order and you say f inverse of f of x, you still get x back. So the order in which you do this composition doesn't matter. You always get x back, as long as you're composing f with its inverse function. Now, one way of seeing this is we know that f to the f of 0 is e to the 0, which is equal to 1. Okay? If I say f inverse of f of 0, well, f of 0 is 1. So this would be f inverse of 1, which means I'm plugging a 1 into this natural log function. So this is natural log of 1. The natural log of 1 happens to be 0. So you go back to the original x value that you plugged in. Right? F composed with f of 0 returns 0. That's true for every x value. Okay? And it's also true regardless of what order you do this composition in. Okay, so we're going to take advantage of these two properties. Okay, so let's look at that first one. So this says f composed with its inverse. Okay, so f of natural log of x. That's the inverse function. Well, what does this give us? Okay, well, when you plug a number into this function, like say 5, then you're just going to get e raised to the 5. Well, in this case, we're plugging in natural log of x, so it's going to give us e raised to the natural log of x. And so you can see e raised to the natural log of x is equal to x by this property. Now there is some restrictions here. Natural log of x is not defined, or it's only defined if x is positive, and that's why we have that restriction. Okay, so that's where that first property comes from. Now the second one comes from composition in the other order. So this says f inverse of f, all right, and f is e to the x. Okay, and if you plug a number into the inverse, like a 7, you're just going to get natural log of 7. Okay, we're plugging e to the x into it, so we're just going to get natural log of e to the x. And you can see natural log of e to the x is equal to x by this property. This one's true for all x values because e to the x is defined for all x values. There's no restriction here. Okay, so that's why that property is true. Okay, so that's where we're getting the first property from. Okay, the second property says that if y is equal to the natural log of x, or y is equal to the natural log of x, if and only if x is equal to e to the y. And that's because they're inverses of each other. So there's two different ways you could write this, right? If you write this in terms of a logarithmic equation, you say that I'm inputting an x and I'm getting a y out. If you want to write this in terms of an exponential equation, okay, if and only if, then you're switching the x and the y, right, when you're working with the inverse. And so now you want to input a y, but you're going to be inputting it into the inverse function of ln, which is base e, exponential function with a base of e. So it's going to be e to the y gives you x back. Now, it may be helpful to come up with an example to show you this. If I say e raised to the 0 power, I get a 1 out. I'm inputting a 0, I'm getting a 1 out. If I write it in terms of its inverse, which is the natural log function, I'm going to switch the input with the output. So now I'm going to input a 1, and I'm going to get a 0 out. And that's just because they're inverse functions of each other. Okay, so again, if you say ln of x is equal to y, then that means e to the y is equal to x. And the easy way to remember this is if you switch these two, then you need to work with the inverse function. Okay, so that's just a property of inverse functions. Okay, the last one says, for real numbers x and b greater than 0, b to the x is equal to e raised to the ln of b raised to the x power, and that's equal to e raised to the x times ln of b. Okay, so first of all, the reason that b needs to be positive is because b represents the base of an exponential function. The base of an exponential function must be positive. So that's why we have this restriction, right? B must be positive because it's a base of an exponential function. Then the power that it's being raised to, which is called x here, that can be any number. It could be positive or it could be negative, right? You're allowed to have negative exponents as well as positive ones. So there's no restriction on this power, which is represented with the x. Now let's see why this is true. Okay, so if you take e raised to the ln of b raised to the x power, then by this property right here, when I do something like this, when I say e raised to the ln of x, I just get x back. So if I'm going to do it here, e raised to the ln of b raised to the x power, then shouldn't I get b raised to the x back by this property? So that's why this is the same as b raised to the x power. And then you can pull this exponent down in front. That's just a property of logarithms. ln of b raised to the x power is the same as saying x times the ln of b. You're allowed to take this power and multiply it in front of the logarithm. And so that's why this is the same as e raised to the x times ln of b. Okay, and we're going to use this later on. So there are times where we're going to take an exponential function with some base, like b to the x power, and we're going to rewrite it so that it looks like this. The reason we're going to do that is because it's easier for us to find the derivative of this function as opposed to this one. So it's nice to write this in this way. So just remember that property later on. We're going to use it when we find the derivative of b to the x. Okay, so this is just some preliminary information that I think you should know before we start talking about finding the derivatives of the logarithmic functions and the exponential functions. Okay, so I hope you found this video helpful. Thank you for watching. Bye-bye.